In mathematics, an exponential function is a function of the form the input variable x occurs as an exponent, hence the name. A function of the form f equals bx plus or minus c is also considered an exponential function, and a function of the form f equals a bx can be rewritten as f equals bx plus or minus c by the use of logarithms, and so is an exponential function. In contexts where the base b is not specified, especially in more theoretical contexts, the term exponential function is almost always understood to mean the natural exponential function, also written as where e is Euler's number, a transcendental number approximately 2.718281828. The reason this number e is considered the natural base of exponential functions is that this function is its own derivative. Every exponential function is directly proportional to its own derivative, but only when the base is e does the constant of proportionality equal 1. The exponential function is used to model a relationship in which a constant change in the independent variable gives the same proportional change in the dependent variable. The function is often written as exp, especially when it is impractical to write the independent variable as a superscript. The exponential function is widely used in physics, chemistry, engineering, mathematical biology, economics and mathematics. The graph of y equals x is upward sloping, and increases faster as x increases. The graph always lies above the x-axis but can get arbitrarily close to it for negative x. Thus, the x-axis is a horizontal asymptote. The slope of the tangent to the graph at each point is equal to its y-coordinate at that point. The inverse function is the natural logarithm lane. Because of this, some old texts refer to the exponential function as the anti-logarithm. In general, the variable x can be any real or complex number, or even an entirely different kind of mathematical object. See the formal definition below. Formal definition. The exponential function x can be characterized in a variety of equivalent ways. In particular, it may be defined by the following power series. Using an alternate definition for the exponential function leads to the same result when expanded as a Taylor series. Less commonly, x is defined as the solution y to the equation. It is also the following limit. Overview. The exponential function arises whenever a quantity grows or decays at a rate proportional to its current value. One such situation is continuously compounded interest, and in fact it was this that led Jacob Bernoulli in 1683 to the number now known as E. Later, in 1697, Johann Bernoulli studied the calculus of the exponential function. If a principal amount of one earns interest at an annual rate of x compounded monthly, then the interest earned each month is x, 12 times the current value, so each month the total value is multiplied by, and the value at the end of the year is 12. If instead interest is compounded daily, this becomes 365. Letting the number of time intervals per year grow without bound leads to the limit definition of the exponential function, first given by Euler. This is one of a number of characterizations of the exponential function. Others involve series or differential equations. From any of these definitions it can be shown that the exponential function obeys the basic exponentiation identity, which is why it can be written as x. The derivative of the exponential function is the exponential function itself. More generally, a function with a rate of change proportional to the function itself is expressible in terms of the exponential function. This function property leads to exponential growth and exponential decay. The exponential function extends to an entire function on the complex plane. Euler's formula relates its values at purely imaginary arguments to trigonometric functions. The exponential function also has analogues for which the argument is a matrix, or even an element of a Banach algebra or a Lie algebra. Derivatives and differential equations. The importance of the exponential function in mathematics and the sciences stems mainly from properties of its derivative, in particular, proof. that is, x is its own derivative and hence is a simple example of a Pfaffian function. Functions of the form cx for constant c are the only functions with that property. Other ways of saying the same thing include: the slope of the graph at any point is the height of the function at that point. The rate of increase of the function at x is equal to the value of the function at x. The function solves the differential equation y equals y. Exp is a fixed point of derivative as a functional. If a variable's growth or decay rate is proportional to its size, as is the case in unlimited population growth, continuously compounded interest, or radioactive decay, then the variable can be written as a constant times an exponential function of time. Explicitly for any real constant k, a function f. Our R satisfies f equals kf if and only if f equals c(kx) for some constant c. Furthermore, for any differentiable function f, we find, by the chain rule, continued fractions for x. A continued fraction for x can be obtained via an identity of Euler. The following generalized continued fraction for Ez converges more quickly, or, by applying the substitution z equals x, y, with a special case for z equals 2. This formula also converges, though more slowly, for z greater than 2. For example, complex plane. As in the real case, the exponential function can be defined on the complex plane in several equivalent forms. One such definition parallels the power series definition for real numbers, where the real variable is replaced by a complex one. The exponential function is periodic with imaginary period and can be written as where a and b are real values, and on the right the real functions must be used if used as a definition. This formula connects the exponential function with the trigonometric functions and to the hyperbolic functions. When considered as a function defined on the complex plane, the exponential function retains the properties for all z and w. The exponential function is an entire function as it is holomorphic over the whole complex plane. It takes on every complex number accepting 0 as value, that is, 0 is a lacunary value of the exponential function. This is an example of Picard's little theorem that any non-constant entire function takes on every complex number as value with at most one value accepted. Extending the natural logarithm to complex arguments yields the complex logarithm log z, which is a multi-valued function. We can then define a more general exponentiation for all complex numbers z and w. This is also a multi-valued function, even when z is real. This distinction is problematic, as the multi-valued functions log z and zw are easily confused with their single-valued equivalents when substituting a real number for z. The rule about multiplying exponents for the case of positive real numbers must be modified in a multi-valued context, but rather multi-valued over integers. See failure of power and logarithm identities for more about problems with combining powers. The exponential function maps any line in the complex plane to a logarithmic spiral in the complex plane with the center at the origin. Two special cases might be noted. When the original line is parallel to the real axis, the resulting spiral never closes in on itself. When the original line is parallel to the imaginary axis, the resulting spiral is a circle of some radius. Plots of the exponential function on the complex plane. Z equals re. Z equals im. Z equals x plus I. Computation of AB where both A and B are complex exponentiation. AB can be defined by converting it to polar coordinates and using the identity B equals AB. However, when b is not an integer, this function is multi-valued, because theta is not unique. Matrices and Banach algebras. The power series definition of the exponential function makes sense for square matrices and more generally in any Banach algebra B. In this setting, E0 equals 1, and x is invertible with inverse E minus x for any x in B. If xy equals yx, then x plus y equals xc, but this identity can fail for non-commuting x and y. Some alternative definitions lead to the same function. For instance, x can be defined as or x can be defined as f, where f, RB is the solution to the differential equation f equals xf with initial condition f equals 1. Lie algebras. Given a Lie group G and its associated Lie algebra, the exponential map is a map satisfying similar properties. In fact, since R is the Lie algebra of the Lie group of all positive real numbers under multiplication, the ordinary exponential function for real arguments is a special case of the Lie algebra situation. Similarly, since the Lie group GL of invertible n times n matrices has as Lie algebra M the space of all n times n matrices, the exponential function for square matrices is a special case of the Lie algebra exponential map. The identity exp equals expect can fail for Lie algebra elements x and y that do not commute. The Baker-Campbell-Hausdorff formula supplies the necessary correction terms. Double exponential function. The term double exponential function can have two meanings. A function with two exponential terms, each with a different exponent such as in e3x minus e4x minus 2. A function f equals AAX. This grows even faster than an exponential function. For example, if r equals 10, then f equals 1.26, f equals 10, f equals 1010, f equals 10,100 equals Google, f equals Googleplex. Factorials grow faster than exponential functions, but slower than double exponential functions. Fermat numbers, generated by and double Misena are numbers generated by examples of double exponential functions. Similar properties of E and the function Ez. The function Ez is not in C. For n distinct complex numbers, A1, and the set, each one Z, ENS, is linearly independent over C. The function Ez is transcendental over C, exp and expm1. Some calculators provide a dedicated exp function designed to provide a higher precision than achievable by using x directly. Based on a proposal by William Kahan and first implemented in the Hewlett-Packard HP41C calculator in 1979, some scientific calculators, computer algebra systems and programming languages support a special exponential -1 function alternatively named x1, expm1, expm, or exp1 meter to provide more accurate results for values of x near 0 compared to using exp1 directly. This function is implemented using a different internal algorithm to avoid an intermediate result near 1, thereby allowing both the argument and the result to be near 0. Similar inverse functions named lnp1, lane1p or log1pu exist as well.